Hello our dear viewers, welcome back to this YouTube channel. Today we are talking about the VSEPR theory, which includes the shapes of molecules. First hand we go. VSEPR theory is used to predict the shapes of simple molecules which attain through covalent bonding. This theory has the following principles which help in determining or predicting their shapes. It's that the pairs of bonding electrons and non-bonding electrons in the outermost shell of the central atom arrange themselves as far apart as possible to minimize the repulsion. The second one, the lone pair repulsion is greater than the lone pair repulsion is greater than the lone pair bond pair, which is also greater than the bond pair repulsion. The greater repulsion between the lone pairs and bond pairs of electrons, the smaller the bond angles, and bond angle is based on the angle between the covalent bonds. In continuation, in some cases when we have double, triple bonds, in determining the shape of these molecules using the VSEPR theory, these double and triple bonds are treated as single charge points or a single group of electrons, or in other words, we look at it as a single covalent bond. However, we should note that there is a very big difference between electron pair geometry and molecular geometry. Here we are going to look at molecular geometries, not electron geometries. So it is the molecular geometries which we are going to look at, and these ones, they define the actual shape of the molecule. First we are going to look at linear shapes. These are the ones which have two groups of electrons. For example, we have only two bonding pairs on one side and another side. So when we compare with beryllium chloride, it has only two bonding two bond pairs. When you look at carbon dioxide, the shape of carbon dioxide is also linear, and the shape of hydrogen cyanide is also linear. However, in carbon dioxide we have oxygen and carbon having double bonds, while in the hydrogen cyanide we have triple bonds. So as we can see that in these bonds we are looking at them as single, we are taking them to be single covalent bonds. That's why the shapes which are attained are linear shapes. Next we shall look at the trigonal planar shape, and these ones have three electron pairs around the central atom, whereby we have no lone pair, and the bond angle which is attained is 120 degrees. We have boron or boron trihydride, sulfur trioxide, nitrite ion, and so many other examples. But the moment when we see only three bonding pairs around the central atom, the shape which is attained is a trigonal planar shape. Next we are going to look at the bent shape, whereby these can have two bonding electrons or two bonding pairs and one lone pair of electrons. Examples is sulfur dioxide, tin chloride, nitrite ion, and so on. We can also have one where we have two bonding pairs and two lone pairs. The examples are as shown below. They also attain a bent or V shape. Next we shall look at the tetrahedral shape. This is one which has four bonding pairs and no lone pairs of electrons around the central atom. The bond angle is around 109.5 degrees. When we can see at the side, when we talk about a tetrahedral, it is this other further side which one is giving us the actual shape of these molecules. In tetrahedral, the tetrahedral has four faces which are all equal. So that is describing these other shapes of methane, sulfate ion, and chlorate 5 ion. Next we look at the trigonal pyramidal shape. These are molecules which have three bonding pairs and one lone pair of electrons. These ones, the bond angle is also approximately that, but can be different according to the type of atoms and the nature which is present. So these ones have one lone pair, and the shape which is obtained is like a pyramid, but with a base of a triangle. That's why it's called it trigonal pyramidal shape. Next we shall look at the trigonal bipyramidal shape. These molecules have 5 groups of electrons around the central atom. 5 bonding pairs, and no lone pairs of electrons. In these molecules, we have bond angles between the bonds 90 degrees, 120 degrees, and 180 degrees. The perfect example is phosphorus 5 chloride. And this is how, on the right hand side, this is how the actual shape looks like if it were put in 3D. Next, we shall look at the seesaw shape. These molecules have 4 bond pairs and 1 lone pair, and our good example is the sulfur tetrafluoride molecule, which gives us a shape of that kind. Next, we shall look at the T-shape. These molecules have 3 bonding pairs and 2 lone pairs of electrons, as we can see in chlorine trifluoride. Next, we shall look at the octahedral shape. These molecules have 6 electron pairs with 6 bonding pairs and no lone pairs. The bond angles exhibited in this molecule, we have 90 degrees and 180 degrees. And on our right hand side, this is how the sulfur hexafluoride molecule would look like if it was to be drawn in 3D. Next, we shall look at the square pyramidal shape. This is one where we have 5 bonding pairs and 1 lone pair of electron. Next, we shall look at the square planar shape. These molecules have 4 bonding pairs and 2 lone pairs of electrons. And one of the examples, or the perfect example, is the xenon tetrafluoride molecule, which have a shape of this. Dear viewers, in conclusion, these shapes of molecules are determined by the nature of the central atom, basing on the number of valence electrons present on the valence shell. We can also determine these shapes by the type of atoms which are bonded to the central atom and the nature of bonding each atom can have. Then the number of lone pairs around the central atom also impact on the shape and the bond angle in the molecule. However, for the learner's need, we are advised to search about more shapes of molecules which have not been included here, and also we should look for the factors which affect the size of the bond angles in different molecules. Thank you for viewing and listening to this educative concept. Let us meet again in my next video. However, I remind you to always share to your friends, like, subscribe, and comment for improvement.